Hello and welcome from Team Plan B of the Google Lunar X Prize. I'm having this chat to let you know that we are rolling out a new program, and that program is Team Plan B's Astronautics Workshop. And we hope that this workshop will give the participants a new set of skills, maybe some experience that we'd like to pass on, that we've grinded out through this Google Lunar X Prize competition, and hopefully it's on the bleeding edge and it will serve well for the participating members. Initially we were planning to bring this workshop and have each workshop with our development work on our Pico satellite, and hopefully we will secure a launch for that Pico satellite, and you'll be able to see our development work, and you can work alongside our development. So right now what I'm going to go over is just the first workshop that we hope to implement, and if there's any interest, you could look at our website, on our website. It will be run by our team lead, Alex, but we will roll out 12 workshops in total, and they are in the range of 3 to 6 months. Again, this all depends if we do secure that launch. But let's take a look at the first one. The first one is more software based with an element of some hardware, and this will be helpful for any software developers that have Java, C# or C experience. We will be looking at the introductory on the trajectory calculation that we're using for as one of our systems, and that will include orbital calculation, optimization of impulses for selection of different orbits, simulation for GPS signals, orbital determination based on distance calculated in the communication sessions. Then we're going to dive in a little bit, skim the simulation of pulsar signals, and orbital determination based on pulsars observation data. That will encompass in the main trajectory calculation. Then we're going to take that trajectory calculation and we're going to apply that with a visual element, and this is where the Java gurus and C# gurus can flourish, and we would like to show you how we are rolling out the visualization aspect of the trajectory calculation that we have in place. And in that visualization we'll obviously have satellite positioning visualization, other celestial bodies, and Earth and Moon visualization. We're going to dive into, again this is all encompassed in the one workshop, we're going to dive into a distributed calculation engine, and we're going to format it in XML. Then we're going to look at our database communication, because if anyone's been following our team, we have our mission control, all encompassing the visualization, the trajectory calculation, the optimization, and what else in the database communication, and you can plug in. Anyways, we'll dive into that a little bit, maybe during the workshop, or maybe in this intro today. And then we're going to take a look at the communication system for our ground stations, and that will encompass the ground station design, central mission control, antenna orbital systems, and communication system for ground station, and time synchronization. That is all in one workshop. Again, this is something that we hope to cover in 3 to 6 months, So there's going to be a number of subsystems that we will look at under the trajectory calculation. The first topic that we will look at is the orbit calculation, and it's analyzing the orbit, and we will look at how you actually define an orbit. Optimization of the impulse for the orbit. Every impulse we'll have to look at it with, we'll analyze to see how we can make it more efficient. And then we get into 3 sections which help us determine where our satellite is. And the first section we're going to look to see how to simulate for the GPS signals, and specifically we're looking at the point where we receive that GPS signal. We need to know how to simulate that in order to test it out, and then eventually we will go live with it. The next orbital determination is based on the distance calculated during the communication system. So every time an envelope is sent from the ground station to the satellite, a certain time passes, and that therefore we could use that data to as a guide of where that satellite is positioned. And lastly, we would look at we need to know how to simulate pulsar signals. All those 3 things, we need to know how to simulate them in order to test out the system before we roll it out to the live environment. So the trajectory calculation piece is really important for the software engineers, the developers, the programmers. It's a piece that you don't get a lot of exposure to on a day-to-day basis. There's not a lot of examples. There's a lot of unknowns. It forces you to, it's challenging. It forces you to think with efficiency. It forces you to grab the latest gadgets out there and start innovating. We highly recommend that piece for any participants that have an interest in or already do have interest, in the software world. Under this trajectory calculation, we also have another section, and that's dedicated to the visualization and satellite positioning. This is an important piece because you know that whole phrase, a picture could speak 1,000 words. Yes, this is a piece that we used for our mission control that we have on our site, and to this right now currently we're using it with Java, and we might look at other tools and might introduce them into that workshop. So the next section that we will look at is the distribution of this trajectory calculation. In order to get exact parameters of the orbit and the celestial bodies, there's some intense calculation that goes that is at play. And what we've done is we've this trajectory calculation. We not only run it in parallel but across multiple platforms and computers in order to provide real-time trajectory calculation while it is in flight. So just to give you an example, before we implement the distributed calculation, in order to calculate a trajectory, it would on one platform, on one computer, it took us a week to get results, where now we're able to do that in a matter of hours. So we will look into that section, part of this, as a part of this. Just to touch on that, last piece, which was the distributive system, the formats of the initial data for the distributive calculation and the end data is in XML format, and that will maybe somewhere down the line someone decides to build a plugin and they can go into different systems, different platforms, and run with that data. There's another element, which is the database element, and any transactions that we have with the satellite and the ground station is logged into the database system. It is run on MySQL. We will look into that, and obviously it's an important piece. We have the data to play with. We could always go back. Obviously everything's supposed to be properly time-stamped, and then we could look into, hey, do we want to normalize this this schema? Do we want to add to it and add another layer or table or relational? So the communication system for the ground station, it is written in C, and it is on the microcontroller. And the microcontroller communicates with mission control through a separate software, which is the ground station. The next section that we go into is the ground station design, and it is comprised of 4 pieces. You have the central mission control, which is written in C#, the antenna orientation system, which is in C and microcontroller, communication system for the ground station, which is in C++, and then we have the time synchronization between mission control and the ground station, which is written in and housed on microcontroller, C and C#. So there you have it. Workshop 1 will look at 19 topics. We hope that the participants are enthused about it, and we hope that this will bring in a good interest. We'll provide the link for this workshop, and thank you for watching.